Hi, welcome back. We're learning about limits and continuity, and now we have the tools to be able to take some derivatives. So when we're dealing with a function of multiple variables, there's not just one derivative, there are multiple types of derivatives. What we're going to start out with is talking about partial derivatives, which form the basis for how we deal with more generic derivatives that are coming up later. So let's set the stage. We have a function f of xy, so a function of both x and y. When we want to take a partial derivative of f with respect to x, then what we do is we take the y variable and we fix it to be a constant. So we take this function that was a function of x and y, we set y to be equal to a number b, and we let only the x variable vary. If you think about that, what that's done is it's replaced every time you saw a y in the function, it replaced it by a constant. And so that means we have a function that only has one variable in it. It only has the x variable in it. And so when we have a function that has only one variable in it, we know how to take its derivative. That's going back to the functions of one variable. Okay, so we have a function. We keep one of the variables and let that vary. Put all the other variables to a constant and take a derivative. We'll do an example in a little bit. How do we notate this? So in many different fields, we're going to have a lot of different ways to write this. We're going to write f sub x of xy. This is the most compact notation. This is the one you just say, okay, so this is saying take the partial derivative of f with respect to x. And this xy here is telling us that we have a function of x and y. We'll be seeing on the next page f sub x of a comma b, and what that represents is it represents taking the derivative with respect to x and then plugging in the point ab. All right, so that's one way to write the partial derivative of f with respect to x. Another way to write it is in this notation. So instead of writing df dx, like we did when f is a function of one variable, here we use this curly d to say it's a partial derivative of f with respect to x. I like to use the word, I like to call that curly d a del. So I would say del f del x. That's my shorthand way to say it. So you may hear that, and that's what that means. It's taking partial derivative of f with respect to x. And if we wanted to say what it was at a point, then we would write del f del x at ab, or we would do del f del x evaluated at ab. So those are some ways that we could write this. Similarly, just like before when we've had this df dx, we'll sometimes think of this ddx as an operator, right? It's a way that we say whatever comes after it, we're taking the derivative of it. So we'll do the same thing here. We'll take del x of f of xy, and that's saying take the partial derivative of f with respect to x. It's really important that we keep that x because we can take partial derivatives with respect to y as well. If we have z is equal to f of xy, then we may write del z del x. And lastly, especially I think in physics textbooks, sometimes you'll see this dx, capital Dx, right? And here again, we're thinking of this dx as an operator that takes in a function and gives out another function that's the partial derivative of f. if we're going to write down the definition of the partial derivative, well, if we think about what happened here, we set y to be equal to a constant. So in terms of our function, we want to see how does a little change in x impact the function. So if we take f of xy and we move a little bit in the x direction, x becomes x plus h. And so the official definition of this partial derivative of f with respect to x is to take the limit as x goes to 0 of f of x plus h comma y minus f of x comma y all over h. So this should look very similar to what we did in single variable calculus. Similarly, if we want to take the partial derivative with respect to y of f, then we set x constant and we let y vary. So we have a little change in y to y plus h, and as that gets smaller, we see how is this differential quotient changing. So let's just do it. Let's take this derivative. So it sounds scary, but it's really not scary. And in no time you'll be able to do this in your sleep. We're all kind of sleeping these days. All right, so f of xy is equal to x cubed plus x squared y cubed minus 2y squared. Here's the function. And so we can ask the question, what is the partial derivative of f with respect to x evaluated at 2, 1? So f sub x is a partial derivative of f with respect to x. And what we're doing is we're saying, let's actually, so that's a function, let's plug in 2 comma 1, and that's going to give us a value. It's going to give you a number. So let's do it. I thought I had a little bit on the next page, but I didn't. So what we do is we take f, we let all the other variables be constant. So if we're taking del f, del x, well, we think of y as a constant, and we think of this as a constant. So the derivative of x cubed is 3x squared. The derivative of a constant times x squared is 2x times that constant. And the derivative of negative 2 constant, well, this is the derivative of a constant, and that is 0. Okay, so let's, while we're in derivative taking mode, let's do this. So the derivative of f with respect to x, with respect to y, let me say. And I'm going to use a blue here. Del f, del y, and this time x is constant. So now x cubed is a constant cubed. The derivative of that is 0. We now have a constant times y cubed. The derivative of a constant times y cubed is that constant times the derivative of y cubed. And then we have minus 2y squared. The derivative of that is negative 4, oops, not x, negative 4y. So we've taken our two partial derivatives. Now we need to plug in our points. So 2 comma 1, what do we get here? We get 3 times 4 plus 2 times 1. So that's 12 plus 4 is 16. And now the derivative of f with respect to y of 2 comma 1, we plug in 2 for x. So 4 times 3 times 1 cubed. And then we minus 4 times 1. So 4 times 3 is 12, minus 4 is 8. And so f sub x of 2, 1 is equal to 16, and f sub y of 2, 1 is equal to 8. All right, let's do another example. G is equal to sine of x over 1 plus y. So if we're taking del g del x, what we need to do is we need to think of y as a constant. So the derivative of this is equal to cosine of the thing plus the derivative of the thing. Right, so how do you take the derivative of a composition? You take the derivative of the outside function, plug back in the inside function, and then you take the derivative of the inside function. And so now we take the derivative with respect to x of this. 1 plus y is a constant, and so we get cosine of x over 1 plus y times 1 over 1 plus y. All right, if we want to take the derivative with respect to y, partial derivative of g with respect to y, what we get is same type of thing. We have to take the derivative of sine of something, so we get cosine of something, and we have to then multiply by the derivative with respect to y of x over 1 plus y. And now we have to take the derivative. The x is the constant, and the 1 plus y is a variable. So what's the derivative of this? So we should probably rewrite this. I'm going to actually rewrite this right now. I'm going to write this as x times 1 plus y to the negative 1. The derivative of that is x plus y, 1, sorry, x is a constant, we can factor it out. And then the derivative of something to the negative 1 power is negative 1, that thing, to the negative 2 power times the derivative of the inside, which in this case, this is just going to be equal to 1, 0 plus 1. All right, so if we wanted to write this nicer, we could. I guess I'll do that up here. We could write this as negative x over 1 plus y squared times the cosine of x over 1 plus y. Right, so we're just taking the variable, we're taking derivative with respect to the variable that we care about, and we're thinking of the other variables as constant. All right, and so we can do this if our functions have more variables than just 2 variables. So the derivative, the partial with respect to x of e to the xy ln of z, well, ln of z is a constant, y is a constant, so what we get is ln of z is just a constant, we're going to keep that out. And then we want the derivative with respect to x of e to the xy. The derivative of e to the something is e to the something, and then we have to take the derivative with respect to x, the partial with respect to x of e to the xy, of the exponent, which is xy. And so derivative with respect to x of xy, derivative of x is 1, and y is just a constant, so we can factor that out. And so the answer, so evaluating this gives us y. We get e to the xy times y times ln of z. On the other hand, if we had taken the partial with respect to z of e to the xy ln of z, what we're going to get is e to the xy is e to a constant times a constant. That's just one big constant. So we can factor that out, e to the xy, and just take the derivative of ln of z, which is 1 over z. All right, so that is an introduction to the partial derivative. The next video will be about the interpretation of what this number means. See you soon.